Okay, so in this tutorial, we are going to pick up where we left off from our discussion earlier in class today on the electric field. So we established that electric fields as a force field that exists between charged objects. We can represent that electric field with field lines that indicate magnitude and direction. And depending on the charge distribution, you'll have different shape field lines, field maps. And then the last thing we left off with is we talked about, well, how do you get a uniform field? A field where no matter where you are, you feel the same strength field and the same direction field. It doesn't happen with single charges or dipoles. It happens with something else. And that's what we're going to pick up with before we go to quantifying field strength. All right, so this one is actually very, very important because there's a lot of applications. And that's uniform electric fields formed between charged parallel plates. Okay, generally the plates are separated by a few millimeters, could be centimeters. We just kind of zoom in on them to exaggerate their distances. And what we have here is a plate that's positively charged on top, negatively charged on bottom, and then we've placed some test charges in here. So if you will, we have our field charges here, which is positive Q. This would be negative Q, and we got our little small q's as our test charges that would respond to the fields. And that's important to keep that distinction because it can get confusing otherwise. So if it's a uniform field, what would the field lines look like? All right, well, we can anticipate that. So if a field line indicates direction, well, then they all have to be pointing in the same direction. We can anticipate that. If I've got positives on top and negatives on bottom, don't write anything just now. If I put a positive test charge there, well, this side's going to repel, this side's going to attract, so we can see that it's going to be downward. Now, in terms of spacing and a number of lines, if it's uniform, what would we expect about the spacing between them? That's correct. They should be evenly spaced throughout. We can arbitrarily choose how wide we want to put it. That would indicate, weaker if it's wider, but we want to keep it uniform. So what we're going to do is, I'm going to come back to the edges in a second. I'm going to start here, draw a field line down. I'm going to go parallel because it's the same direction as the other one. Now I'm going to make sure it's evenly spaced as best as I can for the rest of this. So I'm going to draw 4 arbitrary lines. Now it turns out at the edges, because there's no charges on the outer edges, the field lines start to bow like this. So you should be aware of the edge effect, but that doesn't come up too much. Okay, so that's what we have. If we were to reverse the positive and negatives on the plates, then the field lines would be pointing up. But again, note the consistency with before. We go from positive field charge to negative field charge. Okay, so now we place 2 test charges in there, specifically 2 electrons in the position shown. First question, which particle feels the greater force? Well, the Q on this one, the E1, is a certain value, and the charge on this one is the same value. Okay, so we know we're comparing the same test charge. How about force? Well, if you recall what the whole point of the electric field is, or the uniform field is, it says that it's the same everywhere between the plates. So it doesn't matter where you are, they are going to feel the same force because they are in the same field. It doesn't matter whether one is closer to one plate or the other, or whether they're halfway. That's an important point to remember. It's like if I lift the pen in my hand right now towards the ceiling, its weight doesn't change compared to the floor. If electron 2 is moved towards the bottom of the plate, how would the force change? Okay, so if I move it right there, then hopefully it's fairly evident that it's still in the same field, so there's no change at all. Again, it does not matter that it is closer to the negative plate. You might ask, why doesn't it matter? Well, very simplistic. You might say, why doesn't it feel a greater force there? Well, that also feels a weaker force to the positive plate, and so they always balance out in this geometry. Next question. Okay, for the electrons, how does the direction of the force compare to the direction of the electric field lines? All right. So make sure you understand what the question. The red arrows, which I'm going to redraw, represents the field. It does not represent the force per se. If that sounds confusing, let me explain. The field is due to the plates themselves. Okay, so that's why we're representing them in a particular color, the red. The force is the interaction between the plates and the test charge we put in there. And so the test charge has some say as to what the force is going to be. So what do I have here? Well, an electron is negatively charged. And so which way is it going to be forced? Well, positive wants attractive, the negative plate wants to repel it. So while the field line is down, it is being forced up. Okay, so this is an important thing to remember. When you put a negative test charge in an electric field, the force on it is always going to be opposite direction of the field lines. Why? Because the field lines are based on a hypothetical positive test charge. Well, in this particular case, we have a real negative charge. So we would say its F is up, but the field lines are down. We'll define E a little bit. Okay, if a proton were placed in a field, would any of the above change? So let's say I put a proton right there, a positive. Well, has the field changed? No, because the proton did not give rise to the field, it was the plates. Would the direction of the force field or the field lines change? Again, no, because they're based on something independent of what I put in there. Would the direction of the force change? Well, let's see. The negatives want to attract, the positives want to repel, so it would be forced down. Okay? So that's the only thing that would change from above would be the direction. You might ask, would the intensity or the magnitude of the force change? Well, the big Q hasn't changed. Has little q changed? And the answer is no. It's still 1.6 times 10 negative 19th coulombs. So the only thing that's changed about is direction. All right, I'll answer question 7 in class. I'll show you something on an applet. So let's get to the quantification of the E-field tensity. Okay, so measuring the strength of the electric field. Note that this is not the same as a force. Okay, this is given a symbol capital E. It is like we use that word swag. It is the measurement of the source of the field, whereas force depends on two things. You can't talk about force unless you have two charges interacting with one another. We want to develop a measurement that only depends on the magnitude of the field charge, capital Q, not the test charge, little q. That's a very, very important distinction. And this quantity is called electric field intensity. And I've already mentioned that it is symbolized with a capital E. In gravity, there's gravitational field intensity, which we symbolize with a lowercase g, as opposed to F sub g. All right, so we're going to define it first. Our first equation is a definition of electric field intensity. It's easy, but it's very deceptive. The field intensity, by definition, is the electrostatic force between the two charges divided by the magnitude of the test charge. So I'm going to use QT there. It's not written like that in your AP reference tables, and I'll refer to that later. Okay, so it's force per unit charge. In contrast, little g for gravity was force per unit mass. I'll interpret that more in class conceptually. But if this is the force, Fe is the force between charges, then we can say Fe equals, from Coulomb's law, K field charge times test charge, all divided by the square of the distance. Okay, so note I'm using big Q and little q to differentiate between the charges. The little q in this equation is the same as the test charge in our E field equation, and buried in the F here is the big Q. So let's simplify. I'm going to do it off to the side. So if this is F and I divide by little q for E, I see that these q's cancel out, and I'm left with a more useful definition of E. E is equal to the Coulomb's constant times the magnitude of the field charge divided by the square of the distance. That's an important equation. I'm going to put an absolute value there to indicate it doesn't matter whether you have a positive or negative, you still you don't take that into consideration. So what we're saying is if I make a graph of E as a function of distance, that as you get further and further away from the source of the charge, the field charge, it's going to drop. Also implied in this, if I plot E as a function of big Q, the source of the field, the stronger the charge is, the stronger the field will be for a given distance. And lastly, if I look at E as a function of little q, the test charge, you might be tempted to look at this equation and say there's an inverse relationship there. That's not true, because in this part, there is a little q as well, which we saw canceled out. So if I look at the final equation right here, I don't see a little q in there, so that tells me that the field strength is independent of the test charge. And that's the whole idea of the field strength. Okay? It's based on big Q, not little q. And we'll see that in problems where we have to make distinction. Lastly, we just got to define the units of field intensity. And that can be gotten from the definition. If it's force per unit charge, then the units of force are newtons, and the units of charge are coulombs. So it's newton per coulomb. Okay? So let's do an example real quick to finish up here. All right. Oh, so important notes. E depends on big Q, not little q, even though little q shows up in the definition equation, whereas the force between two charges depends on both magnitudes, as we see in Coulomb's law. The equation does not give any information about direction of the E field. Okay, that must be worked out conceptually, and I'll show that in the next example. Oops. Okay, so what is the field intensity when you're 1 meter away from the static generator? So when I turn it on and charge it, let's say that its charge is 2 microcoulombs. I want to know how strong is the field if I'm 1 meter away from the center. Okay, so what do I know? I'm asking for E, not F. I've got a distance R, and I've got a charge, and I've already labeled that big Q. So we have two equations that have E in it. The definition, F over little q. We don't have either of those, so we're not going to use that. And we have the modification of that, which says E equals KQ, absolute value, all over R squared. Okay, so that's going to be 9 times 10 to the 9th. I'm not going to put the units here. Times 2 microcoulombs. You got to take care of that micro. That's 2 times 10 to the negative 6th coulombs divided by 1 squared. All right, work that out. And we get an answer of 18,000 newtons per coulomb. So what that's saying is, if I stand 1 meter away from that charge generator, for every coulomb of charge that I place there, there will be 18,000 newtons. Now, that's a huge amount of force, but it's very, very unlikely we're going to put 1 coulomb of test charge there. More likely we're going to put a small amount of charge there, so the actual force is going to be more, that's what I want. Drawing a blank. All right, how about the direction? So if I draw our field charge, I drew it as a positive, and what I'm saying is I'm standing we're placing some distance here, R. What direction will be? Well, I can work it out. If I've got a positive field charge, then I'm automatically assuming the test charge is positive. That's a given, so it's going to be away. This is maybe the best way to put it. Not positive or negative, okay, but away from the field charge. All right, how much force is felt at this spot? Well, one of the reasons you want to know about the field intensity is that's a given. At that spot, it's a given number, okay? So I can calculate force just by saying that the force is equal to the intensity times the value of the test charge. Okay, I rearranged the first equation. Well, I just figured this out. I'm looking for this. Do I know the value of my test charge? The answer is no, so we don't know. There's no way of calculating the force unless we know the value of the test charge. So knowing the field charge gives us E, but it does not give us, it's not enough for F. And what would change if QT doubled? Okay, if QT doubled, if I look in this equation, I see that it's not in there, so it does not affect E. So not E. That's a common mistake made. But it would double F. Because if I look at the rearranged form of the first definition, we see that F depends on E and little q. So if I bring in twice the test charge as the original, I'll have the same E field intensity, but I'll have twice the force. Okay, so if you're a little bit confused by that, I will try to straighten that out in class. What I would like you to do is try number 2, just do A and B. We'll do C together in class. Okay, so label all your information, find the appropriate equation. We should be successful with this.